Hi, so I'll be showing you how to derive the arc length formula and how to use it. So suppose we have some y equals f of x function that's differentiable with x being from a to b. We can see that from this drawing. Our curve is this f of x value. And in order to find the length of a small portion, very small portion of the curve, it's like us using the Pythagorean theorem formula with a right angle triangle. You know that a, b, so c would equal the square root of a squared plus b squared, because you know a squared plus b squared equals c squared. So in order to get c, you have to get that square root of a squared plus b squared. On the other hand, if we were deriving ds, ds is really just the change in the derivative of the f of x or the slope. If we had some type of change in x that was infinitely very small and our dy is very small, our actual length of that little small portion, that very infinitesimally small length, or which would be our arc length, is ds. And in order to get ds, we find that it's going to be the square root of dx squared plus dy squared, the way that we derive the Pythagorean theorem with the hypotenuse. So to add up all of these small little infinitesimally small hypotenuses from a to b, we actually have to take the integral of this ds, or change in the slope of the curve. So we actually get that it's going to be the definite integral of the square root of dx squared plus dy squared from a to b. And taking out the dx squared from the formula, we find that our definite integral will be in terms of dx. So we get that the arc length is really just the definite integral of the square root of 1 plus dy over dx squared from a to b. Similarly, if our function was in terms of y, we'll find that the only difference is that we'll be finding dx dy squared, and also it'd be dy, so it'd be in terms of this dy value. By setting arc length in its parametric form, it makes it a lot easier to understand it in 3D when we have to have a z included in the coordinate system. So by setting everything to t, we don't necessarily have to know what dx or dy. So given that we have x equals f of t and y equals g of t, a being less than or equal to t, less than or equal to b, we find that how we derive this formula at the end is first understanding how we get there. So it's just a little bit of manipulating the formulas a little bit. So we know that the dx equals derivative of f of t dt. So if we find the derivative of f of t, we get that it's going to be dx over dt. So we replace that. We find that dx is really just dx over dt times dt. That might look a little bit weird right now, but it makes sense in terms of the formula. So as we learned before, the formula is the definite integral of the square root of 1 plus dx over dy over dx squared dx. So what we want to do is replace this dx and put it right here, and make everything in terms of dt now. So if we do that, and further simplifying our equation by taking out a 1 divided by dx dt, we can cancel out the dx dt that is by the dt. We get that the arc length in parametric form is going to be the definite integral of the square root of the derivative of f of t squared plus the derivative of g of t squared from a to b in terms with respect to t. So this is going to be really helpful, especially when we're going to start learning how to find the arc length in R3. With the arc length formula that I just showed you, let's apply it. Okay, so given that we have some function y equals x to the third power divided by 6 plus 1 over 2x. From the interval, we're trying to find the arc length on the interval 1 to 2, which is x values from 1 to 2. We first want to find the derivative of the function. So we end up getting x squared over 2 minus 1 over 2x squared by finding the derivative of this f of x value. So when we put it into the arc length formula right here, it'd be a little bit easier for us to calculate how to square it. So if we plug this derivative that we just found into the formula, we get this L equals the definite integral of the square root of 1 plus the derivative of f of x squared dx from 1 to 2. So after multiplying everything out and getting this value and subtracting and adding, what we want to do when we get to this step is we want to simplify it so that we can find the definite integral of it. So after making it into a easier form, simplifying it, we get that it's going to be the square root of x squared over 2 plus 1 over 2x squared, the whole quantity squared, and this square root and squared will cancel each other out. So we're really just left with the definite integral of x squared over 2 plus 1 over 2x squared dx. And by finding the definite integral of this, we can definitely find it. And after that, we just plug in our bounds, and we end up getting that the arc length is actually going to be 7 over 12. So definitely try this question on your own without looking at the steps, but this is really just how to calculate the arc length using the formula. I hope this video was helpful in your understanding of how to derive the arc length formula and how to calculate it. Thanks for watching.